Hello. Today we're going to talk about a particular type of quadrilateral called a parallelogram. You're already familiar with a couple of parallelograms, squares and rectangles are two obvious examples. This here on the left, this is a parallelogram. Aside from opposite sides being, I should say, in addition to opposite sides being parallel, that's the definition of a parallelogram, opposite sides are also congruent. And if you think about it, you'll realize that pretty much has to be true. Otherwise they wouldn't be parallel. So it actually goes both ways. If opposite sides are congruent in a quadrilateral, it's a parallelogram, and of course vice versa. Aren't all quadrilaterals parallelograms? Well, no, definitely not. Quadrilateral just has to have four sides, like this one over here. Now this has four sides, but the opposite sides are not congruent, and they sure don't look parallel to me, which makes sense, because if they're not congruent, they can't be parallel. These little arrows here, remember, are designed to show you that the lines are parallel. We put two here to show that this is parallel to this, and one on each one to show that these two are parallel. And of course we use our hash marks to indicate congruence. This one's congruent to this one, not this one. Well, pretty simple so far, right? Remember, all parallelograms are quadrilaterals. If you can figure out how to make a 3 or a 5-sided figure into a parallelogram, do it, and then submit your application for a Nobel Prize. All parallelograms are quadrilaterals, but not all quadrilaterals are parallelograms. Well, that's a good start. What else do we know about parallelograms? Well, we can also say that the opposite angles are congruent. How do we know that? It's pretty easy. We're going to show that and some other things in a minute. Just be aware of it right now, and then we'll get into demonstrating that these things are actually true. May not be a full 2-column proof, it'll be more of a demonstration, more along the lines of show that. They don't do that a lot in this book. Show that and prove that aren't quite the same thing. To show that something is true, it's a lot like a proof, but it's less rigorous, and you pretty much just hit the high points, and the listener or reader is sophisticated enough to fill in the part in between. Whereas a full-blown proof explains every little detail. First, let's see the sense of opposite sides being congruent. First, we draw a little diagonal here. That gives us two triangles. Now, if we can show that these two triangles are congruent, and that these two opposite sides are the corresponding parts of congruent triangles, then boom, we're done. Because corresponding parts of congruent triangles are congruent. Now, how are we going to do that? We're given that these two horizontal lines are parallel. So this angle here and this angle here must be congruent. They're opposite interior angles. It's also true that this angle is congruent to this angle for the same reason. They are a pair of opposite interior angles. So we have two angles that are congruent. That's enough for similarity, but not enough for congruence. We need a side. Well, wait a minute. This side is shared by both triangles, so it must be congruent to itself. So now we have angle, side, angle. So both these triangles are congruent. Now all we have to do is match up corresponding parts. Well, this angle, the opposite side from this angle is this one here. Let's put a little line there. But the opposite side from this angle is this angle here. So these two sides are the corresponding sides of our congruent triangle. Pardon me, our pair of congruent triangles. This line, of course, is congruent to itself. These two segments, I should say this segment is congruent to itself, and these two segments are congruent. And of course, these two are also congruent. Now that we know that we have two congruent triangles, and we know that every side on this triangle is congruent to some side on this triangle, we just have to figure out what the corresponding parts are. And we just did that. These opposite sides are the corresponding parts. So this side is congruent to this side, and that side's congruent to that side, because this diagonal produces two congruent triangles. Okay. But there's a bunch of other stuff we could show about this too. For instance, we showed that this angle, well, they're two congruent triangles, right? And this angle is congruent to this one, this angle is congruent to this, so these are the corresponding angles of the congruent triangles. Well, which angle corresponds to this one? This one does. This opposite angle here is the corresponding part to the congruent triangle over here. Or we could also say that this is the angle opposite this side, and this is the angle opposite this side. Match them up that way if you like. Either way, this angle must be congruent to this one. Again, that's because we drew our diagonal and created two congruent triangles. And once we have two congruent triangles, we can find all kinds of things that are true, such as the congruence of opposite sides, the congruence of these two opposite angles. What about these angles? Well, I happen to draw the diagonal, the long diagonal you could say, because when we smush this down and turn it into a skewed parallelogram, not a rectangle or a square, but still a parallelogram, this would be the shorter diagonal. However, if I had drawn this short diagonal, we would still have a transversal cutting two parallel lines. Opposite interior angles would still be congruent. They would still share a side, which is the diagonal. And the two triangles I created with this diagonal would also be congruent by exactly the same reasoning that the two triangles I created were congruent when I drew this diagonal. In other words, the short version of that usually in mathematics is by symmetry, because there's really no difference between drawing the diagonal this way or this way for purposes of this little demonstration. So by symmetry, it's also true that this angle here and this angle form a pair of congruent angles also. I'll leave that to you. You can go ahead and draw yourself a parallelogram and then draw the diagonal this way, and you'll see that you've created two congruent triangles. So we know the opposite sides are congruent. We know the opposite angles are congruent. What else can we show here? And for these two opposite angles, you could also say that we have that this angle here is made up of two angles. This angle is made up of two angles. It's the sum of two congruent angles. So these must be congruent also. In other words, this angle here is congruent to this one. This angle here is congruent to this one. If this were A and this were B, then this angle is A plus B and this angle is A plus B. That's another way you could look at it to see that these two opposite angles were congruent. I might have mentioned before that there's more than one way to arrive at the correct answer. There's another little fact of parallelograms, which is consecutive angles are supplementary. In other words, alpha plus beta equals 180. And if we had a beta prime over here, you could say alpha plus beta prime was 180, and if we had an alpha prime over here, we could say alpha prime plus beta prime, alpha prime plus beta. Any two consecutive angles, their measure will add up to 180. Why would that be true? Well, for instance, for these two, here's two parallel lines. You've got this upper horizontal and the lower horizontal line. They're parallel. Consider this side a transversal. What do we have? We have interior angles here. Pardon me. These two angles here are consecutive interior angles, if we think of this as our transversal. And we already know from our chapter on parallel lines and transversals that these two interior angles are supplementary. And again, by symmetry, we could consider these two lines here, our two shorter sides, to be the parallel line, and think of this top horizontal line as your transversal. Well, then these two, now these two are the consecutive interior angles, and they're supplementary. You want to look at these two? Well, exactly the same argument you used, or I used, when we cut these two lines with this transversal. Now we're cutting the same two lines with this transversal. You can go all the way around like that. Cut these two parallel lines with this transversal, and then these become consecutive interior angles. So, any two consecutive angles in a parallelogram. Sound like I got a mouthful of cotton, don't I? Really, I was sober all night last night. I don't know why. I mean, I don't know why I sound like I got a mouthful of cotton. I know why I was sober. I didn't want to wake up hungover, that's why. Any two pair of consecutive angles, we're going to add up to 180. Now, we'd like to show that when we have two diagonals in any quadrilateral, they break, each one breaks the other one up into two congruent parts. In other words, this part is congruent to this, and this is congruent to this. You could say that each diagonal is a bisector of the other. It's not a perpendicular bisector, but it does bisect. This diagonal bisects this one, and this diagonal bisects this one. Well, how the heck do we know that's true? Well, we can spot some angles, congruent angles and sides pretty quick here. And when we do that, we're going to use the same argument we've used pretty much all the way through. Congruent triangles. Once we show that we have some congruent triangles, then we can show that the corresponding parts of the congruent triangles are congruent, and we're pretty much done. So let's find a couple of congruent triangles. What about this one and this one? Well, let's see. Alternate these, we have these two horizontal lines here are parallel. We're given that. That means this is a transversal, and it means that this angle and this angle form alternate interior pairs. So they're congruent. Well, we have another transversal here. So the alternate interior pairs for this transversal are this and this angle over here. Okay, we've got two angles that are congruent. If we knew that this side here in between these two angles, these two sides were congruent, we'd have congruent triangles by the angle side angle theorem. Wait a minute, we already proved that opposite sides are congruent. In fact, that's why I put that little hash mark there, so we wouldn't forget. So now we have angle side angle congruent, and the two triangles are congruent. Now all we have to do is match up the congruent parts. For instance, this side here is opposite this angle. So this one would be congruent to what? Well, this is the angle that's congruent to this. Here's the side opposite that angle, so... Oh, wait a minute. If this side of this triangle is congruent to this side of this triangle, these are just the two segments that were created when we cut this diagonal with this diagonal. In other words, we've cut this diagonal, created two congruent segments, which is pretty much the definition of a bisector. So this diagonal definitely bisects this one. What about this diagonal bisecting the other one? Well, I'll let you do that. By symmetry, it's going to work out exactly the same. Use your alternate interior angles theorem combined with the fact that we already know that opposite sides are congruent, and boom, you're going to get that this segment over here is congruent to this segment here. So what do we know about parallelograms? Number one, they're always quadrilaterals. Number two, their opposite sides are parallel. Pardon me. The opposite sides are congruent. We also know that opposite angles are congruent. That would be the whole angle here, not the split angle. The angle that's split by the diagonal here. Forget the diagonal. This whole angle here is congruent to this angle. This side is congruent to this side. Opposite sides are congruent. Opposite angles are congruent. What else? Consecutive angles are supplementary. And the diagonals bisect each other. That's 4 important facts we're going to use to work problems on parallelograms today. So let's do some. Now there's an example of how we can use one of the properties we just demonstrated. Find angle B. Well, that's a consecutive angle. What do we know about consecutive angles? We know that and measure of angle B equals 180, or measure of angle B equals 180 minus 51. I think that's 129. Yeah, that's 129. So if just remember your properties, and a lot of these problems are going to be very simple. This one obviously is. I'm sure your 7-year-old cousin could probably do this one, as long as he remembered that these two angles add up to 180. Well, this problem, of course, could be done in a number of ways, but we just had a theorem which said that the diagonals bisect each other. They say they intersect at point M. Well, all we have to do is find a bisector for one of these segments, or, in other words, the midpoint of either of these segments. Which one do you like? It looks like they both have numbers that we can just look at and see what they are. In other words, for instance, M, it's kind of hard to tell what it is. It's a little to the right of this line here at 1, and it's somewhere in between 2 and 3. It doesn't tell us much. This one here looks to me like it's right on the corner with an x-coordinate of -2 and a y-coordinate of 5. And down here we have an x-coordinate of 4 and a y-coordinate of 0. And how do we find the midpoint? Remember, we take the average of the x-coordinate and the average y-coordinate. So if we try that over here, we got -2 plus 4 over 2. Why am I finding the midpoint? Because diagonals bisect each other, so they intersect at the midpoint. And 5 plus 0 over 2. Well, -2 plus 4 is 2 over 2 is 1. And they didn't reduce the fraction here. We'll just leave it as 5 over 2. Does any of these match? Oh, well, there we go, first one. So the answer would be A. As I said, there's probably more complicated ways to figure out what this point is, but now that we know diagonals intersect at the midpoint, all we needed was a little bit of arithmetic. Once again, your 7-year-old cousin probably could have done this if you explained to him what a midpoint was. Here we have a parallelogram, ABCD. We're given that one side is 14 inches and the adjoining side is 20 inches. If they had said the opposite side was 20 inches, we could stop right there, because in a parallelogram, opposite sides have to be equal. And if they tell you that you've got a parallelogram and one side is 14 inches and the opposite side is 20 inches, just walk away. That can't possibly be true. So it has to be that our consecutive sides are 14 and 20 respectively. Well, what does that mean? You could say that this is 14 and this is 20. And that means that just like with a rectangle or a square, the perimeter is going to be 2 times the width plus 2 times the length, which works out to 2 times L plus W, or 20 plus 14 is 34, times 2. Oh, and there's 68 right there. Once again, these problems are extremely easy, so long as you recognize the properties of parallelograms. Here's one that, I don't know, we could draw a picture, but let's see if we can work it out without actually making reference to the picture. First, we have to interpret what it is they're saying. One interior angle of a parallelogram is 50 degrees, period, which is more than 4 times the measure of another angle. Well, I don't think that's the way they mean it. I think they mean to say that one angle is 50 degrees more than 4 times the measure of another angle. That's the way I'm going to interpret this. So what the heck does that mean? One angle is 50 degrees more than 4 times the measure of another angle. Well, suppose we just choose x as the measure of another angle. Well, that's 4x so we're going to assume that one angle is x and some other angle is 4x plus 50. Well, opposite interior angles are congruent, which means we can only have 2 different measures in a quadrilateral, in a parallelogram. So what we have is that 2 times this angle plus 2x, which is the other angle, adds up to 360. Remember, a parallelogram is still a quadrilateral, and the interior angles have to add up to 360. So, we've got ourselves an algebraic equation, don't we? You've got 8x here. Go ahead and expand this. Plus 100 or we get that 10x equals 260. So I would say, pretty easy to see, that x equals 26. 4 times 26 plus 50. Let's see, 4 times 26 is 104, isn't it? So this one here, the 4x plus 50. I don't know. Well, I started the parentheses, I might as well put them in. 4x plus 50 equals 4 times 26, is that 104? Plus 50 equals 154. Does that work? 2 times 26 would be 52. 2 times 154 would be 308. Plus 52 would be 360. So it works. So really, the only important part to this problem was remembering that the interior angles of a parallelogram add up to 360. That, in interpreting this sentence here, allows you to lay out an algebraic equation, which you then solve fairly easily. Okay, we have another one of those problems where a couple of politicians from a state that will remain nameless have taken up geometry. The dynamic duo of inseam and flea bite. Now, according to them, we're not sure whether it was inseam or flea bite who decided that if angle B is 50 degrees, angle A must be 50 degrees. Well, in parallelogram ABCD, notice A and B are right next to each other. That means AB is one segment. That also means that angle A is not opposite angle B. This would be 50 degrees. Not this one. Consecutive angles, remember, they're supplementary. So this would be, well, I think I drew this wrong. If this was 50 degrees, this would be like 130. Obviously, this is the larger angle. So I should have drawn it skewed the other way. Let's accept the fact that this is not drawn to scale. The point is, consecutive angles are not congruent. Opposite angles are. Consecutive angles are supplementary. So, once again, inseam and flea bite have done it all wrong. This one, we should be able to do it without actually drawing a diagram. We know that A, B, C, and D are the corners of a quadrilateral. We don't know whether it's a parallelogram or not. Well, they say it can't be, but I think it would make more sense to just say is it or is it not, and then explain why or why not. We'll do it their way. Angle A and B are consecutive, so they have to be supplementary, because in a parallelogram, consecutive angles are supplementary. 124 plus 66. Well, I don't think that adds up to 180, does it? Let me double check. Frankly, for my money, we could stop right there. Why? Well, the way that we proved that consecutive angles were supplementary would make it impossible for non-supplementary angles to be part of a parallelogram. Why? Well, these two are parallelogram. That means, pardon me, these two lines are parallel. So, alpha plus beta add up to 180. But alpha plus beta add up to 190, which is a contradiction. And so by contradiction, these two lines can't be parallel. Or there's another way we could do it. Again, we could add, well, let's see here. Angle B and angle C would be consecutive angles. Like, whoa, 124 and 124 is definitely not going to be add up to 180. So once again, that's a second reason that they can't be a parallelogram. What about the opposite angles here? We have A here. This is, yeah. A and C have to be equal, or congruent. And they've got A at 66 and C at 124. So opposite angles have to be congruent if it's a parallelogram, but they're not. That's a contradiction. Consecutive angles have to add up to 180, and neither pair of consecutive angles add up to 180. That's two more reasons, or two more contradictions, which say that these lines can't be parallel. So there's about three different ways you can say that this is not a parallelogram. Now here's one where they've asked us to use a, well, I don't know if they told us to actually use a coordinate plane, but it seems like the simplest way to actually work the problem out. We're given three of the points, and we're asked to finish off the fourth point and produce a parallelogram. Oh, they did tell us to use a coordinate plane. Okay, good for them. Well, here's one possibility for turning these points into a parallelogram. We just have to find point D over here somewhere. How do we do that? Well, this side is parallel to this side, and this side is parallel to this side. If we want to find this point, there's another way we could do it, of course. We could find the slope of this and the length, and then we could take a line that starts here, has the same slope, and ends at the appropriate point to have exactly the same length as this segment here. But that would probably involve more computations, definitely require the distance formula. This will probably be easier. We'll find the equation for this line that's parallel here, because we have a slope and a point on the line. And then we'll find an equation for this line, because it'll have the same slope as this one, so we know the slope and one point on the line, and where these two lines intersect, that'll be point D. So let's do that. What's the slope of, well, I should probably label these so that we know what the heck we're talking about. And C. So what's the slope of BC? That would be, let's see here, 6 minus 3. It's not 6 minus 3, pardon me, it's 6 minus 4. That's the rise. 6 minus 4. And 3 minus 6. That's the run. Or the change in y over the change in x. Either way, it's minus 2 over 3. It's actually 2 over minus 3, but I think it's easier to just write minus 2 over 3. The same thing. And over here we get 4 over 2, which is 2. That's the slope of this section here. So the slope of BC is minus 2/3. The slope of AB is 2. Now all we have to do is work out the equation for this line. a line which is parallel to AB but passes through C, and the equation for a line which is parallel to BC but passes through A. Well, now that we have our slopes from here, we can work out the equation for the two lines. We got, remember, A is the point 1, 2, and the other point we knew was the point 6, 4. So we take 2/3 times 1 plus B equals 2. And when we work that out, we'll get an equation for our line y equals minus 2/3 x plus 8/3. Same thing here, we'll get the slope, and we know one point. This time we're going to use the point 6, 4. 2 times 6 plus B equals 4. B equals minus 8, so we get this. That's our equation for the other line. Now, where do these two lines intersect? Well, when these two equations are equal. So we do a little rearranging, solve the equation, and get that x equals 4. Now we can put that into either equation and get our y coordinate. 2 times 4, well, that's 8 minus 8, which is 0. So one of the points that works for D is 4, 0. And if I draw my segment from here to 4, 0 and here to 4, 0, well, it certainly looks like a parallelogram to me. We could double check, but I don't think there's any reason to. I'm willing to believe this is a parallelogram and that this is the correct point. The fact is, there are other ways to come up with the parallelogram, though. For instance, in this one, I connected AB and BC. I could have connected AC now. Just a second ago we connected the lines up this way and found this point here. But there are other ways to connect the points A, B, and C that we were given. Well, there's another parallelogram we can find by connecting A and C. Before we connected AB and then BC, and then came down here and found D down in here. Now we're going to connect AC and this and figure out where these two lines intersect. This has the same slope as this one, and this has the same slope as this. So what have we got? Well, for BC we get a slope of minus 2/3, just like we did before. For AC we get a slope of 4 minus 2, pardon me, that's 2/5, over 6 minus 1. That's 2/5. Well, now all we have to do is find the equation for this line and this line. For this line we have a slope of minus 2/3 times 1, that's our given, our x-coordinate from our given point on the line, plus B equals 2. That's the y-coordinate for the point given on the line. From that we solve for B and get that B equals 8/3. Next, we do the same thing with this line here, which has a slope of 2/5. This is the point on the line, so we can write 2/5 times 3 plus B equals 6. That's what I wrote here, and that leads to B equals 24/5. Now we have an equation for the line. This line up here is going to be 2/3 x plus 8/3. The equation for this line is 2/5 x plus 24/5. We need to know where those intersect and do a little rearranging and get that with the common denominators, 16 over 15 times x, and then subtract the 24 over 5 from each side, and get that 40 minus 72 over 15 for the constant over here. That ends up being minus 32 over 15 equals 16 over 15x. We can cancel the 15s. As we divide through by 16, we're going to get that. We put it, well, x equals minus 2 right here. Now we can put that into either equation, and we'll get 4. Exactly the same as we did it when we were finding point D down here. Now, there is still one more parallelogram we can find, I think. I believe we can connect this side and this side. No, that won't work. There is one more way to get a parallelogram out of these 3 points. We can extend off this way, so that this line is parallel to AB, and this segment is parallel to AC. Once again, we would, to get the slope of this, we just find the slope of this one. For the slope of this, we find the slope of this one. We use a point on the line to get B. Use a point on this line to get the other B. We set the two equations for the line equal, and we get the intersection point here. And guess what? I'm going to leave you to do this one here. Just do exactly what I did for the first two, and you shouldn't have any trouble finding point D out here. Well, that's about it.